Get ready to torque your nuts, harden your gears, and forge your mind into a bulletproof study guide. We are mechanical engineering made simple. Okay, so let's unpack this. Today we're really diving into the nitty-gritty of gear design.
Right. We're talking everything from the basic names for parts of a tooth all the way up to, advanced manufacturing and figuring out when they might fail using real data.
Exactly. And the goal here isn't just to list terms. We want you to get the intuition behind it.
Yeah, why does an engineer pick this shape or that steel? These choices affect everything. Efficiency, noise, how long the gear lasts, it's all connected.
Let's start with the absolute basics, the language. You've got two gears meshing. How do we name them?
Simple. The smaller one is always the pinion.
Always the pinion. Got it.
And the bigger one, we just call it the gear. Straightforward.
And that size difference immediately tells us the ratio.
Correct. Number of teeth on the gear, divide that by the number of teeth on the pinion. That gives you the gear ratio.
And that ratio conceptually links to the pitch diameter, doesn't it?
It does. The ratio of the pitch diameter's gear over pinion is exactly the same as the tooth ratio. The pitch circle is just that imaginary circle based on the pitch diameter, where the mating happens.
Okay, now measuring the size of the teeth themselves, this is where we hit that split between systems, imperial versus metric.
Right. In the U.S., mostly you'll hear diametral pitch, or DP.
And DP is, how's that calculated again?
It's the number of teeth divided by the pitch diameter, usually in inches. So you might see DPs from like 1/2 up to 200.
And the key thing to remember with DP
is that it's kind of inverse. A bigger DP number means a smaller, finer tooth. Think less load, maybe smoother, potentially.
Now, inverse relationship. Got it. And the metric side.
Like that's the module, usually written as dollar.
And nodule is?
It's the pitch diameter, this time in millimeters, divided by the number of teeth. So it's a reciprocal of DP, essentially.
Which means a larger module number.
A larger, chunkier tooth. More load capacity, generally. Modules typically range from, say, 0.2 up to maybe 50.
Okay, so size is set by DP or module. Now let's look vertically at the height of the tooth relative to that pitch circle.
Right. Two key terms here. The height above the pitch circle. That's the addendum.
Addendum above, okay.
And the depth below the pitch circle is the dedendum.
Dedendum below. And there's a standard relationship there, isn't there? The dedendum isn't the same as the addendum.
Exactly. The dedendum is deliberately made larger, about 25% larger in a standard tooth.
Why is that?
For clearance. You absolutely need space at the bottom of the tooth gap. If you use the imperial math, the total height, the whole depth, is like 2.250 divided by the diametral pitch. That extra bit in the dedendum ensures the tip of one tooth doesn't crash into the root of the mating tooth.
No crashing. Good plan.
Definitely. That clearance is vital.
Okay, this is where, for me, it gets really fascinating, the actual shape of the tooth profile. We mostly use the involute curve now.
Yes, the involute is king. And it's such an elegant piece of geometry. Imagine unwinding a taut string from a cylinder or a base circle. The path traced by the end of that string. That's the involute curve.
And why that specific, slightly complex shape?
Because it solves a fundamental problem beautifully. It guarantees a constant velocity ratio between the gears. Smooth power transmission. And crucially, it maintains this smooth meshing even if the center distance between the gears isn't perfectly exact. It's forgiving.
That tolerance for error must be huge in manufacturing and assembly.
Oh, absolutely. It's a cornerstone of modern gearing.
And tied into that involute profile is the pressure angle. Usually 20 degrees, you see that number everywhere.
Yep, 20 degrees is the modern standard.
Yeah.
You used to see 14.5 degrees more often, and sometimes you see higher ones like 25 or even 27 degrees for specific applications.
So why did 20 degrees win out? What's the trade-off?
It's that classic engineering compromise. A lower pressure angle, like 14.5, gives you more teeth in contact at once, a higher contact ratio. That means smoother, quieter running.
But there's always a but.
But the tooth root is significantly weaker. It's more prone to bending failure, and undercutting becomes a bigger issue.
Okay, so weaker tooth. What about a higher pressure angle, like 25 degrees?
Stronger tooth root, definitely. Much more resistant to bending. But you get fewer teeth in contact, a lower contact ratio. That tends to increase noise and vibration.
Ah, so 20 degrees is the sweet spot. The best balance between strength and smooth, quiet operation for most applications.
Exactly. It's the go-to compromise that works well in most situations.
Okay, so we've designed this perfect geometric tooth, but geometry means nothing if the material cracks under pressure. Let's switch gears, no pun intended, to materials.
Right. Steel is the dominant player, no question. But there's a huge range within steels.
Like what?
Well, for applications where cost is a big driver and the loads aren't extreme, you'll use low-carbon, low-alloy steels. Basic, reliable stuff.
But when you need performance, small package, lots of power, like in an EV gearbox.
Then you have to step up. High-carbon, high-alloy steels. They cost more, but they give you the strength and hardness needed for that power density.
You also mentioned bronze in the outline. Seems a bit old school compared to high alloy steel. Where does that fit?
It's specific but important. Think worm gears. In a worm gear set, you have a lot of sliding contact, not just rolling.
Ah, high friction situation.
Very high friction. Bronze has excellent low friction properties, good wear resistance against steel. So it's often used for the worm gear, the larger wheel, meshing with a steel worm. We call these tribological applications, focusing on friction and wear, sometimes in bimetal parts too. But yeah, its overall strength isn't close to steel.
Okay, so steel is chosen. But the raw steel isn't usually strong enough, right? Heat treatment is key. You mentioned two main approaches, through hardening and case hardening.
Correct. The core difference is depth. Through hardening heats and quenches the entire gear uniformly. You might get a consistent hardness, say Rockwell C42, all the way through. Makes it tough, resists shock well.
But for wear, high speeds, high loads.
That's where case hardening, often carburizing, comes in. You're diffusing carbon into just the outer surface layer of a low-carbon steel.
Creating like a hard shell.
Exactly. You heat treat it to get an extremely hard outer case, maybe up to Rockwell C60, fantastic for wear resistance. But crucially, the inside, the core, remains softer and tougher.
And that softer core is important, not a weakness.
No, it's vital. The hard case handles the surface contact stress and wear. The softer, more ductile core absorbs shock loads and prevents the whole tooth from just shattering like glass if it gets hit hard. It's the best of both worlds for many high-performance gears.
What about really big gears? Is case hardening practical then?
It gets really slow and expensive for very large parts. So for those, induction hardening is often preferred. You use electromagnetic induction to heat just the surface layers quickly.
And you mentioned a specific advanced technique, simultaneous dual frequency induction, or SDF. What's the benefit there? Two frequencies.
It's about targeted heating. On a gear tooth, you care about hardness on the flank surface for wear, and you care about strength deep in the root to prevent bending failure.
Two different requirements, two different locations.
Precisely. SDF uses a high frequency that mainly heats the very surface, like the flank and tip, and a lower frequency that penetrates deeper to heat the root area more effectively. By blending these two frequencies simultaneously, you get precise control over the heating pattern.
So you can optimize the hardness profile for both wear on the flank and bending strength in the root at the same time.
That's the goal. Maximize both properties, which was tough to do well with single-frequency induction. It's a big deal for high-stress gears.
This level of detail carries right into manufacturing. You group methods into generating versus forming. What's the classic generating method?
Hobbing is the workhorse. You use a cutting tool, the hob, that looks kind of like a threaded worm. It rotates and feeds across the gear blank, and its motion generates the involute tooth profile. Very efficient for high-volume production of standard gears.
But less flexible.
Traditionally, yes. Setting up a hobbing machine for a specific gear takes time. That's where the newer CNC methods shine.
Like invo milling.
Exactly. Inbo milling, multi-axis CNC milling. These use standard cutting tools on flexible CNC machines. The machine's computer calculates the complex tool path needed to cut the involute profile, or frankly, almost any profile you can define mathematically.
The flexibility is the key advantage.
Huge advantage. You can switch from making one type of gear and a completely different one almost instantly just by changing the program. You can make prototypes easily, or even produce complex geometries that were basically impossible before.
Like the example you gave of bevel gear with a cosine-shaped tooth line.
Yeah, stuff like that. Things that hobbing just can't do. Yeah. It opens up design possibilities.
Okay, so we have amazing materials, precision manufacturing, but gears still fail. What are the common ways they break down?
Two big ones dominate, especially in hardened gears. First is pitting.
Pitting, like little craters on the surface.
Exactly. It's surface fatigue. The repeated high contact stress, right where the teeth mesh, eventually causes tiny cracks to form just below the surface. These cracks grow, and eventually a little piece of material flakes out, leaving a pit.
Is pitting always catastrophic?
Not always. Sometimes you get initial pitting during run-in, where the high spots wear down, the load distributes better, and the pitting stops progressing. But severe pitting can definitely lead to failure or noisy operation.
And the second failure mode, you mentioned it's a bigger concern for case-hardened gears.
Right, that's tooth flank fracture, or TFF. This one is trickier.
Why trickier? Where does it start?
Unlike pitting, which starts at or near the surface, TFF starts deeper within the material, below the hardened case. It initiates in the transient zone, that boundary layer between the super hard case and the softer core.
Ah, related to those residual stresses from heat treatment.
Precisely. If the heat treatment process leaves unfavorable residual stresses deep in that transition zone, fatigue cracks can start there, even though the stress from the gear mesh is highest at the surface. Once started, the crack propagates outwards, often leading to a large chunk of the tooth breaking off suddenly. It's a major focus of current research.
So, if TFF is driven by these internal stresses and the case core boundary, how do engineers design to prevent it and also tackle the other big issue, noise, especially vital in EVs now?
A key technique is profile modification. This sounds weird, but you intentionally deviate slightly from the perfect involute profile.
Wait, you deliberately make the shape slightly wrong.
And slightly and strategically. Techniques like crowning, making the tooth slightly convex across its width, or tip and root relief, chamfering the profile slightly near the tip and root.
Why on earth would you do that?
Because real gears aren't perfectly rigid, and shafts aren't perfectly aligned. Under load, teeth deflect, shafts bend a little. If you have a perfect involute, this deflection can cause the edges of the teeth, or the tips, to dig in hard at the beginning or end of the mesh cycle.
Ah, causing high stress concentrations and noise.
Exactly. By adding relief, you give the tooth profile a little room to accommodate that deflection smoothly. It prevents edge loading, reduces the dynamic kick as teeth enter and leave mesh, which significantly cuts down noise, and it helps to distribute the load more evenly across the flank, improving surface durability.
But there's a limit, right? Too much modification.
It's just like having a large manufacturing error. It can reduce the contact ratio or cause other problems. It's a very precise adjustment.
And related to geometry, we also need to avoid undercutting. What's that?
Undercutting happens during generating processes like hobbing, especially with low tooth counts or certain profile shifts. The cutting tool essentially scoops out too much material at the base of the tooth below the active profile.
Weakening the tooth right where the bending stress is highest.
Precisely. It severely compromises the tooth's bending strength. It's a geometric limitation you have to design around.
All this ties into NVH, noise, vibration, harshness. It's not just about strength anymore.
Absolutely. NVH is often the driving design constraint, especially for passenger vehicles. Engineers now use sophisticated analyses looking at things like peak-to-PE transmission error, tiny fluctuations in the output speed caused by the meshing geometry and deflection. Minimizing that error is key to quiet gears.
Okay, another term that often causes confusion, backlash. Sounds bad, like something's loose.
It is looseness, but it's intentional and necessary. Backlash is simply the amount by which the width of a tooth space exceeds the thickness of the mating tooth. It's that little bit of rotational play you feel if you hold one gear still and wiggle the mating gear.
And why is that necessary?
Two main reasons. One, thermal expansion. Gears heat up in operation, and they need space to expand without binding. Two, lubrication. You need that tiny gap to allow the lubricant film to form and be maintained between the sliding rolling surfaces. Without backlash, the lubricant gets squeezed out.
So zero backlash gears, which you hear about for precision applications, are they running dry?
Not necessarily, but achieving it requires cleverness. You can use special gear types like duplex lead worms or spring-loaded mechanisms or very precise manufacturing with minimal tooth thinning. But you have to be careful.
Especially with worm gears, you mentioned.
Yes, zero backlash is generally bad for worm gears because of the high sliding component. You really risk wiping out the lubricant film, leading to galling, seizure, and rapid failure. You need that backlash for the oil wedge.
Makes sense. And lubrication directly impacts efficiency, right? Especially at high power.
Hugely. In many high-power gearboxes, the energy lost to gear sliding friction churning the oil essentially can be the single biggest source of inefficiency.
Wow, more than bearing friction or other losses.
Often, yes, especially at higher speeds and loads. So choosing the right lubricant viscosity and type is critical not just for wear protection, but for minimizing those churning losses and keeping temperatures down. Bad lubrication leads to heat. Heat lowers viscosity. Lower viscosity reduces film strength. It's a potential downward spiral.
Okay, let's pull back to the big picture. We've gone from tooth profiles to metallurgy to failure modes. How is all this knowledge being used in the real world operationally?
The big trend now is moving beyond scheduled maintenance to truly proactive maintenance, using real-time data.
So sensors on the gearbox feeding data back?
Exactly.
That,
Modern vehicles, industrial equipment, they collect telematic data constantly. Speed, measured torque, operating temperature, vibration signature sometimes.
and what happens with that data?
This is the cool part.
Yeah.
That raw operational data gets fed into sophisticated simulation models, often the very same finite element or fatigue models that the engineers used to design the gearbox in the first place.
So the simulation runs using real-world load cycles instead of theoretical ones.
Precisely. The model takes the actual measured torques and speeds and temperatures, and it calculates the cumulative fatigue damage, predicts the remaining life, maybe estimates the growth rate of a potential TFF crack based on the actual operating conditions.
Wow. So it's converting real-time operational data into a predicted reliability or remaining useful life.
Yes. And that prediction isn't just logged somewhere. It's often presented directly to the operator or maintenance team, maybe via a mobile app or dashboard. It might say, component nearing end of life, schedule replacement, or high stress detected, inspect lubricant.
So it allows maintenance before failure based on actual usage, not just hours run.
Exactly. It accounts for operational variability. Maybe one truck driver is much harder on the transmission than another. This system captures that difference. It's moving towards maintenance based on condition and prediction, often fully automated, providing incredible insight.
That's quite a leap from understanding the addendum height and the dedendum clearance.
To choosing specific alloy steels and heat treatments like SDF hardening to resist TFF.
And finally, using telematic data fed into the original design models to predict failure in the field before it happens. Incredible integration.
And underpinning all of it are the industry standards. Decades of research, testing, failures, successes, all distilled into standards like AGMA here or ISO globally.
Like ISO 6336 for bending strength calculations, or ISO 1328-1 for tooth tolerance quality grades.
Those standards are the common language. They ensure that whether you're designing a tiny gear in Switzerland or a massive industrial gearbox in Germany, the principles for calculating load capacity, for defining manufacturing quality, are consistent and reliable. It allows global manufacturing of complex systems, like EV powertrains, with predictable performance.
It really makes you think how even seemingly simple choices made decades ago, like standardizing on that 20-degree pressure angle, created a foundation that enables the complexity and reliability we see today. It ensures that engineers everywhere are more or less speaking the same mechanical language.
A universal language of cogs and teeth, built on physics and refined by experience.
Until the next equation, design junkies, we are mechanical engineering made simple.